line structures and ground clearance. Ground clearance. The minimum clearance of live conductors from ground and building at different places as per IE rules. And see what are the ground clearance from different voltages for low tension line, that is less than 650 volts, that is 5.79 across any street, and for 11 kV line it is 5.46 along any street, 4.55 meters that is erected elsewhere. That is for HT line, that is 650 volts to 33 kV, we are known as HT high tension lines, that is 6.07 meters per across any street, and along any street that is 5.79 meters and 4.55 elsewhere erected. For 33 kV to 130 kV extra high tension lines, across the line is 6.07 meters, along any street is 6.07 meters, and erected well elsewhere is 6.07 meters. The minimum ground clearance for extra high tension line is 6.07, but that is up to 20 inches. Beyond 132 kV, that is 132 kV to 220 kV, that is 7.012 meters for across the line and along the line related where that is 7.012 meters. Here the ground clearance shown in the figure. The ground clearance to the 11 kV line. See here. Ground clearance to the road. Factors on which conductor spacing and ground clearance depends. Factors affecting where ground clearance and spacing. So there are many factors which on the conductor spacing and ground clearance depends. At voltage, span and weight of the conductor SAG. Voltage means when the voltage levels of the conductors plays the crucial role in determining the conductor spacing to decrease the mutual induction between the conductor and earth. The conductor spacing is directly proportional to the system voltage as right. So the conductor spacing to decrease the mutual induction. The conductor spacing is directly proportional to the given system voltage. Already we have discussed it on the previous slide. Then is for 21 kV, it is the ground clearance, and 3 kV, another kV, 20 kV, it is the ground clearance. Next, span. The conductor spacing is decided not only by the electrical concentration of working voltage, but also such mechanical factors such as span and weight of the conductor and SAG. And common conductor spacing for 11 kV, 33 kV and 66 kV lines. Common conductor spacing for 11 kV, this is 66 kV towers. Here, see here the A point is conductor insulator to insulator. The difference between insulator to insulator. What is the spacing for 11 kV, it is 0.914 meters. For 33 kV, it is approximately 1 meter. At 66 kV, that is 1.8 meters. See here this insulator to insulator distance. Here insulator to insulator distance. That is here the first one is 11 kV and 33 kV, next one is 66 kV. Yeah, 0.914 meters and approximately it is 1 meter and 1.8 meters. B means the spacing between the conductor to conductor. Spacing between the conductor to conductor 1.35 meters and 1.5 meter and 2.4 meters. Here C is the extra line voltage, that is 66 kV. The conductor to conductor insulator spacing is 0.914 meters and 1.05 meters and 1.8 meters. And for the HT lines from 66 kV to 400 kV, the conductor spacing depends upon the configuration of the conductors. Common conductor ground clearance adapter for 11 kV, 33 kV, 60 kV. That is across the street is 5.8 meters for low tension lines, and 11 kV 5.8 meters and 33 kV 6.1 meters, and for 66 kV it is 6.1 meters. And along the street is 5.5 meters for low tension lines and 5.79, 5.5 meters, 5.5 meters and 6.1 meters along the street. Other areas there is erected where 4.6 meters, 4.6 meters and 5.2 meters and 5.5 meters. So we are discussing about what the factors on which conductor spacing and ground clearance depends, and common conductor spacing adapter for 11 kV, 33 kV, 60 kV, and common ground clearance adapted for rail lines 11 kV, 33 kV, 60 kV. So once I am explaining here, what is the ground clearance? The minimum clearance of live conductors from ground and buildings at different places. The minimum clearance of live conductors from ground and buildings at different places as per IE rules. For LD it is 650 volts. For low voltage 5.79 meters and 5.46 meters, that is along, and others that is 4.55 meters. For 650 volts to 33 kV, it is 6.07 meters and 5.79 meters and 4.55 meters. For 33 kV, 102 kV, 6.07 meters, 6.07 meters and 6.07 meters. For 130 kV to 220 kV, 7.012 meters along and across the street and others. The ground clearance in road, that is for different voltages there is different ground clearance. factors on which the conductor spacing and ground clearance depends. That is voltage. That is the main important role in the voltage. That is voltage level of the conductors plays a crucial role. Determine the conductor spacing to decrease the mutual inductance. The conductor spacing is directly proportional to the system voltage and locality. Depending upon the local area, the conductor spacing is more in order to avoid short circuits during heavy winds. In residential area, the density of trespassers by is more. The conductor spacing is decided by not only by the mechanical factors such as span, weight of the conductor and wind direction. The conductor spacing is already we have discussed for different voltages, span and weight of the conductor and SAG. Here the common conductor spacing adapted for 11 kV, 33 kV and 66 kV lines. Here the spacing between the insulator to insulator is A means, and B is the spacing between the conductor to conductor spacing, and C is the for a HT line that is up to 66 kV, the spacing between the insulator to insulator. For LT 11 kV lines, that is 0.914 meters. For 33 kV it is 1 meter and 1.8 meters. And B conductor, that is spacing between the conductor to conductor, is 1.35 meter and 1.5 meter and 2.4 meters. That is for 11 kV line 0.914 meter, 1.05 meters and 1.8 meters. And common ground clearance adapted for 11 kV, 33 kV, 66 kV lines is across the street is for low tension line, that is 5.8 meters. For 11 kV it is 5.8 meters. For 33 kV it is 6.1 meter and 6.1 meter. Along the street, that is 5.5 meter and 5.5 meter, 5.5 meter and 6.1 meters. Other areas, elsewhere erected areas, that is 4.6 meters, 4.6 meters, 5.2 meter and 5.5 meter. So still now we are discussing about factors on which conductor spacing and ground clearance depends, and common conductor spacing adapted for LT 11 kV, 33 kV, 66 kV lines, and the common conductor ground clearance adapted for 11 kV. In this class we are discussing about definition of SAG, factors affecting the SAG. What is SAG? The difference in levels between points of support and the lowest point on the conductor is called SAG. The difference in levels between points of support and the lowest point on the conductor is called SAG. That means here it is the one pole, here it is another pole, in between there is a conductor, here it is the SAG. The difference in level between, here it is a conductor, but actually the conductor is not in horizontal, slightly there is a because of the tightness we are giving a loose connection between the bones, that is known as SAG. The difference in level between points of supports and the lowest point the conductor is known as SAG. Here it is the lowest point. is known as SAG. The vertical distance between points of supports conductor and the lowest point of the conductor. Here it is point A, here it is point B. That is point A means one pole, point B is another pole. The distance between A and B points of supports and the ground clearance between the points is known as SAG, the lowest point of the conductor. Here it is the lowest point of the conductor, that is known as SAG, at equal levels of supports. Here it is unequal supports. Points of supports, that is point A and point B, SAG at A, SAG at B. So the lowest point of the conductor is at different levels point of supports. Here it is the lowest point of the conductor is known as SAG. When an overhead line conductor is hung between two supports, the conductor takes natural catenary shape. The difference in levels between points of supports and the lowest point of the conductor is known as SAG. It is important to note that the overhead line conductors must be under safe position. The conductors are too much stretched between supports in a bid to save conductor material. The stress in the conductor may reach unsafe value, and in certain cases the conductor may break due to excessive tension. In order to permit safe tension in the conductor, they are not fully stretched but allowed to have a sag or dip. So that's why here the lowest point is known as sag. When the supports are in equal position, and here the red line is indicates the conductor, and the points A, B is the tower pole. Right? If the total distance between two poles is x distance, we are assuming is here at lowest point to conductor A and B is half of its length. That is, if suppose the length is x, the lowest point to the pole is x by 2. If the conductor is supported between same level point of supports, it takes a shape of catenary. Lowest point is at middle of the span, that is x by 2. Tension at any point on the conductor acts as tangential. And here the total length is x, and W is the weight of the conductor per meter length, that is kg per meter. T is the tension on the conductor, that is tension is always opposite to the conductor, that is middle point, lowest point is O, and S is the sag. Tension at supports is approximately equal to the horizontal tension acting at any point on the conductor, that is T is equal to T naught, where T is the tension at any point of the supports. Now, what are the factors affecting the factors to be considered while mechanical designing of overhead lines? Right? SAM should be kept to a minimum, sufficient clearance above the ground level. And different points about SAG. When the conductor is suspended between two supports at the same level, it takes the shape of catenaries. However, if the sag is very small compared with the span, then sag span curve is like a parabola. If the sag is very small compared with the span, then sag span curve is like a parabola. The tension at any point on the conductor is tangential in the tension T at the lowest point. O acts as horizontally. The horizontal component of tension is constant throughout over the length of the wire. The tension at support is approximately equal to the horizontal tension acting at any point on the wire. If thus T is the tension at the point B, then T is equal to T naught. And what are the factors affecting the sag? The various factors affects the sag in overhead lines. That is weight of the conductor. Heavier the conductor, greater will be the sag. So if the conductor weight is more, the sag will be high, and vice versa. In cold places where ice coating takes place, the conductor weight increases and the sag is increases, and distance between adjacent poles and levels of point of supports and wind pressure. Greater the wind pressure, there will be the swing and the sag is increases. So here still now we are discussing about definition of sag. Definition of sag or the factors affecting the sag. The difference in levels between points of supports at the lowest point on the conductor is known as sag. Difference in levels between points of supports and the lowest point on the conductor is called sag. Here it is the lowest point. So this is the conductor. This is the lowest point on the conductor. Here it is sag. The vertical distance between the points of supports, the conductor and the lowest point on the conductor. The vertical distance between the point of supports, conductor and the lowest point of the conductor. That is, point A is the one pole and point B is another pole. Thus, the length of the conductor should be not in straight line. Because of this tightening the conductor break occurs. The conductor should be breaks. So that's why we are using here some loose band that is known as sag. That is the point of supports. Dip, that is known as sag. Sag or dip, both are same. Lowest point of the conductor. At equal levels of supports, different levels of supports. If the one pole is very short and the other pole is very high, the distance between these poles is unequal supports. And this sag at A and sag at B. That is the lowest point of the conductor. Right? Next definition of sag. Here it is, the point A and B is the points between the poles, and the length of the conductor should be here x. For equal length, that is the lowest point of the conductor is the point between lowest point to the pole is, that is half of its length, that is L by 2. T naught is the tension, that is horizontally and O is the middle point of the SAG, lowest point of the conductor. Here a conductor and points of supports. The conductor is supported between the same level of point. The supports takes a shape of catenary. If the conductor is supported between same level point of supports, it takes as a shape of catenary. The lowest point is middle of the span is x by 2 or L by 2. The tension at any point on the conductor acts as tangentially. That is T naught is it acts as horizontally or tangentially, that is T naught. The tension T naught at the lowest point acts as horizontally, and tangential means it acts as downwards. Horizontal component of tension is constant throughout the length of the wire or conductor. Horizontal component of tension is constant throughout the length of the conductor. Tension at any supports is approximately equal to the horizontal tension acting at any point on the conductor. Tension at supports is approximately equal to the horizontal tension acting at any point on the conductor. Where T is equal to T naught, where T is the tension at any point of supports. B. Factors to be considered while mechanical designing of overhead lines. That is, the SAG should be kept at a minimum and sufficient clearance above the ground level. When the conductor is suspended between two supports at the same level, it takes the shape of catenary. When the conductor is suspended between two supports at the same level, it takes the shape of catenaries. However, if the SAG is very small compared with the span, then the SAG span curve is like a parabola. The SAG is very small compared with the span length, then the SAG span is like a parabola. The tension at any point on the conductor acts as horizontally, tangentially. Thus, tension T at lowest point O acts as horizontally. See here. First point is when the conductor is suspended between two supports at the same levels, it takes the shape of catenary. Catenary means here it is the two poles. Here it is the SAG. Right. When the conductor is suspended between the two supports at same levels, it takes the shape of catenary. Catenary means like this. Right. Next, however, the SAG span is very low. The span curve is like parabola. The supports is very low. The SAG span is like this. So it is under the shape of parabola. Right. The tension at any point on the conductor acts as tangentially, thus T and the lowest point acts as horizontally. Means here it is tension acts as tangential, that is at point O, it acts as T naught and O. The horizontal component of tension is constant throughout the length of the wire. The horizontal component of tension is constant throughout the length of the wire. The tension at supports is the approximately equal to the horizontal tension acting at any point on the wire. The tension is at supports is the approximately equal to the horizontal tension acting at any point on the wire. Thus, if the tension T is at the point B, is the T is equal to T. And what are the factors affecting the SAG? Right. main what the factors about in SAG is and weight of the conductor. The weight is more, the SAG is always more. The heavier the conductor, the greater will be the SAG, and vice versa. In cold places where ice coating takes place, the conductor weight increases and so SAG is also increases. And the length of the span, as the span increases, the SAG also increases. That is, SAG is directly proportional to SAG, right? And tensile strength, the SAG is inversely proportional to the tensile strength. And temperature, as the temperature increases, the length of the conductor also increases, so the SAG also increases. Pressure, wind pressure, greater the wind pressure, more will be the swing, and the SAG is increases. The distance between the adjacent poles, level of points of supports, and wind pressure. So we have discussed about definition of SAG, direction of tension acting on the conductor, and factors affecting the SAG. We have discussed in the class there is definition of SAG and factors affecting the SAG. So in this class we discussed about derivation of SAG equation, equivalent levels of supports. Calculation of SAG. The tension is governed by the conductor weight, effects of wind, ice loading, the temperature variations. Now calculate the SAG and tension in the conductor, that is, supports are at equal levels. The levels of supports, that is levels of poles between the two conductors, will be same. Here it is the pole, here it is another pole. The level of this pole should be same. The SAG is, as this point is O, horizontal tension, that is length of the conductor is L by 2, and W is the weight of the conductor, right? Supports are at equal levels. Let the length of the span, that is L meters, and weight of the conductor is W kg per meter, and lowest point of the conductor is O, and the tension in the conductor is kgs T. Right here the length of the conductor should be in L, and that at lowest point the conductor size is L by 2. Right. Consider a point P. Consider at a point P on the conductor at a distance x from the point O. The curvature OP is so small that the curved length equal to its horizontal projection. That is, here consider a point P here. Consider a point P here. Here the curvature OP is very small. Consider as it is horizontal distance, that is, here it is the distance is x distance, right? And it is horizontal vertical component, that is y, right? Consider at point P the distance x meter from O, that is considered point P. The conductor distance of x meter from the point O. The curvature OP is very small, so it is the equal length is equal to horizontal projection. That is, here the two forces acting, assume the distance between OP is almost equal to x, and the vertical component is y, and the weight of the conductor is W into x, acting downwards at x by 2 distance. In between the OP, the lowest point is x by 2, that is x by 2, and the tension T acting at O, and the moment of two forces is about point O. That is, then the two forces acting on the portion OP are the tension T acting at O, the tension T acting at O, and the weight of the conductor OP acting downward at x by 2 from the point O. That is, so equating the moments of two forces at point P, that is the tension in the vertical plane is T into y, that is equal to, what is the force, W into Wx into, what is the distance, x by 2. So here the two forces acting about the point O, one is vertical component and one is horizontal. One vertical component is T into y, and the horizontal component is Wx into distance, it is x by 2. That is, y is equal to W into x square by 2, and T, Wx square by 2T. Y is equal to Wx square by 2T. Here, the maximum SAG is represented at the either the supports of A and B. At point P, at point B, x is equal to L by 2 and y is equal to SAG. X is equal to L by 2, y is equal to SAG. Substitute these values in y is equal to Wx square by 2T, that is y is equal to S, W is equal to x means L by 2, and is L by 2 whole square by 2T, that is equal to WL square by 4 by 2T, 4 into 2 is 80, so WL square by 80. Here W is the weight of the conductor, L is the length of the conductor, and T is the tension acting at point O, and S is the SAG. So once again explaining a derivation of SAG. The tension is governed by the conductor weight, effects of wind, ice loading, and temperature variations. Now calculate the SAG and tension of a conductor when supports are at equal levels and supports are at unequal levels. Here first one is supports are at equal levels. When the two supports are equal, the length of the conductor should be L, and at point O, that is SAG, the length of the conductor should be L by 2, and here the T is tension acting in horizontal conduction, and W is the weight of the conductor should be in downwards direction. Let the length of the span L meters and weight of the conductor is W kg per meter, and the tension in the conductor is T kgs. At lowest point the conductor is O. Here the point O, the equal length of the line is L by 2. At point P, here OP is the curvature is very small, that the curved length equal to its original horizontal projection, that is OP is equal to the distance is x, right? At point P the vertical component is y, the horizontal component is, and weight of the conductor means that is W into x. The length of the conductor should be x by 2. The total length is x at point P, half of its length, that is x by 2 length. Consider at point P the distance x meter from O vertical distance is y from P. Assume the distance between O P is almost equal. This the curvature OP is almost equal to horizontal plane, that is x. Here the weight of the conductor Wx acting downwards at W by 2. The weight of the conductor is acting as Wx, that is W by 2. The tension T acting at point O. Moment of two forces about point O. The tension T acting at O, then the weight of the conductor OP acting downwards at x by 2 meters from the point O. So equating the moments of the forces at point P, we get that is horizontal force and vertical force. That is horizontal force is, that is T into y, tension into vertical plane, that is T into y, is equal to what is the weight of the conductor, that is Wx into distance is x by 2. Wx into x by 2. Here Ty is the vertical plane force and Wx into x by 2 is the horizontal plane. So from this we get the value y is equal to Wx into y is equal to Wx square by 2 into T. W is equal to Wx square by 2T meters. At point P, the length of the conductor should be x, that is equal to L by 2, and the y is equal to s. At point P, the length of the conductor x is equal to L by 2 and y is equal to s. Substitute these values in. Y is equal to Wx square by 2T. So y is nothing but s is equal to W, x is nothing but L by 2 whole square by 2T. So s is equal to W into L square by 4, 2 square 4 by 2T, that is 4 by 4 into 2, 8T. So s is equal to WL square by 8T. So supports B, that is length of the conductor x is equal to L by 2 and the y is equal to s. So SAG is equal to s is equal to WL square by 80 meters. So in this class we are discussing about length of this conductor, ground clearance, conductor spacing, what are the factors affecting the conductor spacing and ground clearance, and what are the factors affecting the SAG, and SAG equation where the supports are at equal levels. So in this class we are discussing 3 topics. So when the supports are at unequal spacing, the SAG is equal to S is equal to WL square by 8 into T. Here S is the SAG and L is equal to length of the span in meters and T is equal to tension. So next class we are discussing about when the supports are at unequal levels and the SAG effect of wind and ice and different problems on SAG. So here it is, the derivation of SAG is very important in our diploma. So that is SAG is equal to WL square by 8. So in this class we are discussing about what are the factors affecting the SAG and SAG equation at same levels. Okay, thank you.